Okay, so from this point forward, the recording is in progress. I want to first review a little bit on the ORS mini-series itself and its importance, organization, and goals. This will give us a little bit time also if there are more participants going to join. First of all, why OpenAirInterface Studio mini-series is important and why we are doing this. For these particular 5 reasons: to share knowledge with our community, identify new challenges and features towards 6G, accelerate R&D procedures and life cycles from the idea process to proof of concept and demo. This is the main type of use case that are used with our product OpenAirInterface Studio, which then later could be completed by adding the MX PDK product that continues from that proof of concept demo towards more R&D activity and towards the direction of production. We could showcase ideas and validate use cases that are discussed in community, and at the same time foster academia and industry collaboration and use this advantage of research. OpenAirInterface Studio is a full solution by itself, is one of our products in our product family that you see here, MX ORS, PDK, and Pro. This MX ORS is mainly, the main use case is for learning and R&D procedure, and it relies on a lot of different emulators and simulators. We have also the MX PDK product that uses the real radio, and it is more suitable towards R&D and proof of concept towards TRL5 to TRL7. And finally, the Pro product, which goes to official deployments using the RUs TRL9. All of these solutions, they use the same consistent UI UX, the same platform and tool chain. So you would see the different, my colleagues would use different types of deployments to run the system, but all of them, they share the same software, the same source code that are consistent across each other. This could run on different types. You could have it on a single PC, on a private cloud, or on a hybrid cloud, public cloud, for example, and on different type of deployments, on bare metal deployments and containerized deployments and Kubernetes deployments, for example. In a nutshell, what would be the procedure that you go forward with OpenAirInterface Studio as per se as a product is that you focus on design and development of your own use case and your network. Then you do deployment, and you could do also customization on that. It comes with also measurements and test toolboxes that you could do end-to-end measurements, including the throughput, latency, and also onboarding applications that we would see in the different demos. And finally, perform analyze and evaluation based on the outputs, or using, for example, the tools such as Wireshark to see the messages. OpenAirInterface Studio is, in fact, the world's first production-grade cloud-native platform that seamlessly designs, operates, and experiments on emulated end-to-end 3GPP and O-RAN standard. What does it mean is that it doesn't use the traditional simulated type of platform, but it has the emulation of the full stack, and that full stack, the only part that is emulated is practically the radio channel that goes through the radio emulation. The rest of the stack is fully executed as if it was running in a normal mode. It also supports edge services, and it could run at a scale following DevOps principles. In terms of the features, it supports, as I said, multiple infrastructures. You could run bare metal, on-premise, public clouds, single node, etc. It supports the SMO. It comes with SMO and the RIC stack, including non-RT, near-RT, and OEM. It helps you to do network design, protocol tracing, log extraction, integrated UI testing. It comes with RApps and xApps for monitoring and control, which you could also use the SDKs to extend it for your own RApp and xApps. It has the end-to-end agile and a scalable declarative deployment, which includes the user equipment in the loop, meaning that in case of the emulated UI, which is the main application of the OpenAirInterface Studio, this UI is also responsive to your SMO and OEM subsystem. It includes a lot of day 2 features, including network reconfiguration, upgrade, and fault management beyond the control actions that you could make with the RIC subsystem. It's important to note the difference between the declarative subsystem that this ORS is based on and imperative deployments that you find in a lot of different tutorials that you need to install a bunch of different packages and build it from source, or all that other troubles that you're not facing in here. The multi-vendor support in our system includes OI, SRS, and Open5GS, both in LTE and NR, but also recently we have integrated the more production-ready subsystems such as Lighton, as is one of our vendors that we would see in the future slides. It comes with programmable cloud-native observability using the Grafana dashboard, including a multi-source data lake that contains the RAN, energy, and infrastructure metrics. Some of the use cases that are very useful to be used for O-RAN Studio are in terms of education and training, which one huge example of it is that we are using this for training students and at Eurocom for 2 consecutive years. The data collection and model training, very useful for the AI/ML, the emerging AI/ML applications. The RAP and xApps design and analysis could be done also for the different use cases. Interoperability testing has been performed on the platform successfully by, for example, bringing the xApps that are written on the other RIG platforms, as long as they use the same E2AP version and architecture. The test and measurements with the UE in the loop are done here, and this overall helps you to do research validation. And since it has the ability to reproduce the same results consistently across the different platforms, this would automatically also bring reproducibility into your research that could be validated by other partners that are using the same platform. And this, in total, gives you a very best tool of the network simulation and emulation. In total, this creates a vast ecosystem of end-to-end, both in the direction of from the UE to the core network, including the UE user application, edge, RAN, and the core network. And from west to east, that includes the RAN, near-arteritic, xApps, non-arteritic, and SM1 RAPs. This goes across different radio technologies. We see 4G, LTE, 5G, NR, SA, and NSA, different vendors, including industrial grade such as Amarisoft and Lighton, open source such as OpenAirInterface, SRS, and Open5GS, on top of different radio devices. So I mentioned O-RAN Studio works is more on the emulation part, so RF simulator, but the MX PDK package extends this O-RAN Studio towards also using the radio devices such as different type of SDRs, USRP from National Instruments, DIME SDR, AW2S, RRH, Lighton, RU, and Amarisoft SDR. For doing the xApps and RAPs, you could use various types of programming languages, C, C++, Python, and Golang. We have a bunch of examples on each of the languages. When it comes to containerization, there are various types of container technologies that you could use, and it runs on different operating systems, cloud infrastructure, and all of these, they're encapsulated in a concept that is coined by BubbleRAN called multi-X, meaning that whenever it comes to a choice, you have the freedom of choosing whatever type of a stack that you want. This applies to different type of use cases, from xApp development to maintenance, vertical users, and business intelligence, that you see some of the examples of the xApps and RAPs that applies in each of the cases in here. I suggest you to refer to our other videos on YouTube that they deeply explore this type of use cases, from education, research, to testing and measurement, data analysis, and optimization. Today, we are going to have this short agenda of in two parts. The first part would focus on the BubbleRAN's MX-RIC ecosystem, and it would dive deeper into O-RAN's 3 pillars that are moved towards 6G in terms of KPM, RC, and CCC service models. Then we would have like a 5 minutes break, and then we would have the second part on OpenRAN and Gen AI and generative AIs, and then the last part would be discussion beyond O-RAN and how we are moving towards the road into 6G. Today, I'm your host. I'm the product manager from BubbleRAN. You see me on the right side. My name is Ali Reza. We are going to have Mikhail as the leading presenter he is a principal engineer from BubbleRAN. He would lead the most of the technical discussion, and we would have 3 demo presenters that are from right to left. Ilyas, he's a PhD student at Eurocom, expert in SMO and generative AI. Kai is a RIC developer from BubbleRAN, and Chichen she's a PhD at Eurocom, that expert in O-RAN all the O-RAN related topics. Now I would leave the floor to my colleague Mikkel. He's in the call to continue the technical discussion now on MX-RIG, which is the BubbleRAN's RIG ecosystem. I will stop sharing to allow him to share a screen, and I would be in the chat responding your questions. Thanks.
So, hello everybody. Can you see my screen?
Yes, Mikkel, your screen is clear. Please go ahead.
Okay. So, my name is Miguel. I'm going to be talking about the MX-RIG today and how it is the BubbleRAN's RIG ecosystem. So, OpenRAN and heterogeneous networks, basically they are a symbiosis, right? I mean, OpenRAN is about the standardized interfaces that you can interoperate in different parts of the network seamlessly and securely, right? Regardless of its origin, right? And on the other hand, we have a standard interfaces from one side, and from the other side, we have what we call it multi-X or heterogeneous networks. We can think it in this way. We need to have multi-vendors. We need to support from femto to macro cells. We need to support different architectures. We need to support ARM, x86, FPGAs, maybe also different splits. Yes, we may need to support O-RAN 7.2, E1AP, for instance, if we want to separate the CPUP and CPCP, the F1AP, if we want to separate the DU and the CU. If you want to go through a more thorough discussion regarding multi-X, here we share a link so that you can go there. So BubbleRAN's MX-RIG, it's based on FlexRIG. The kernel is basically FlexRIG, and up to today it is the most complete near real-time RIG and E2agent open source O-RAN specification. The design of this multi-X, you can see it on different dimensions. It is multi-rad, so you have 4G and 5G. This was from the beginning, thought like this. It supports different hardware architectures, so ARM, x86, and the reason is that it was developed with C11. We didn't use any intrinsics, right, to accelerate some of the most time-consuming functions. We didn't use that. And we don't even use like compilers extensions, just very little of them. It has been multi-version since the very beginning. So we use a static polymorphism. We use generics of C11, if you're aware of. Basically, at compile time, you can choose if it is an E2AP, version 1, version 2, version 3, or you can, for instance, for the KPM, we use the same. Same applies for the not just the versions, but also the encoding. If you want to encode it ASN1C, if you want to use flat buffers. And the idea is to avoid the pointer-to-pointer-to-pointer chasing, right? That is this, it would be this dynamic polymorphism that actually the compiler has difficulties, yes, to create good and fast software for it. It has been multi-language from the very beginning, C, C++. At BubbleRAN, we support, Python is in FlexRIG supported, but BubbleRAN, it also supports Golang, and this is thanks to the SWIG. So we could also like easily extend it to other languages. For instance, like Java is easily doable, or JavaScript. We are right now multi-vendor. My colleague Ali Reza, he mentioned OAI, srsRAN, Amarisoft, Lighton. This has been easily doable actually because the software was easily and was well maintained, right? Right now, the BubbleRAN MX-RIG is complete. We have KPM, RC, and CCC service models. We are following the zero overhead principle, the same as FlexRIG here. So we have a small footprint. You don't pay for what you don't use. So at compile time, you can decide like which base station, which database you want, which encoding you want. I mean, we try to maintain this as small as possible. This makes it fast, and we try to avoid all the external dependencies, all the data structures and algorithms I wrote them back then for FlexRig, so we have no dependencies. FlexRig it is also delivered with SDKs, and this is to facilitate xApp development with simple and intuitive APIs. We try to be as simple as possible. If you have been doing FlexRig, you would probably know that you just need init, try to stop. You can subscribe to get some data, remove that subscription, or send the control message, right? 5 calls easily. We try to maintain the best practices on maintenance, so we run it with the address sanitizer and the thread sanitizer. We use a static analyzer such as CPP check or scan build, client ID. We do some code coverage with GCOP. We do testing. We use different compilers. We use GCC. We use Clang. We use also different linkers. I mean, we try also to get preconditions and post conditions in nearly every single function. So the first thing that you will see is like assertion, which basically we try to follow these preconditions. We try to follow the solid principles as much as we can, right? With single responsibility, open close, least scope principle, interface segregation, which is pretty important, and dependency injection that we don't use it that much since we use static polymorphism for it. Now, how does FlexRig compares to the near real-time rig proposed by the O-RAN Alliance? So it is based on microservices. The idea of microservices, it emerged like a decade ago. It was not, the idea was to try to follow this single responsibility idea to the end, right? So everything will be like a process. It will communicate to other processes through normally sockets, right? And we will try to avoid basically coupling of the software that it was shown in the industry that if you just leave software for some time, yes, coupling, the software, it starts getting worse and worse with the time. There are different problems with this pattern. It is not recommended nowadays that much. However, the disadvantages that we have with the near real-time rig of the O-RAN Alliance, it's beyond, I think, the design, right? I mean, it's a resource hungry, so you need quite a lot of RAM and memory to run it. You are incurring high latency, higher complexity, and than what you should be, since you are not following the zero overhead principle, right? Everybody needs to pay for it, right? You could have just a function call, which is very fast. Instead of that, you need to go through all the network stack, right, to send a message. Unfortunately, it's not very thoroughly tested, right? We have found some problems there. It's not really following the solid principles. I think that if you have been like programming the near real-time rig, or at least what I found the worst, it was, for instance, that when you are writing an xApp, you are also responsible for encoding, decoding the E2AP protocol, but also the service model, right? So you need to put a lot of code actually on the xApp to be able to manage it. So the interface is definitely not well defined there. It is even difficult to run it as a simple Docker container, right? I know that people from srsRAN, they have been trying this and fighting for getting this. I think that they have something now, but I don't think that it's been an easy path for them. In theory, microservices, they allow greater flexibility since you can change different services easily, right? Since in theory, the interface is the network, so you don't have coupling. So here we do a little comparison with the release I. So they don't follow the zero overhead. Everybody needs to pay, even if you don't use it. I mean, even if you are in an embedded system, you cannot really run it on an embedded system, right? Because you will need the Kubernetes and you will need a lot of resources. On the contrary, you can run MXRig. It's not a problem. For encoding and for decoding, we follow this open principle. So right now there is ASM1C, flat buffers, plain, but you could easily add a new encoding or decoding scheme. E2AP versions, we support a bit more. E2AP messages, the rig supports, the O-RAN rig supports the bare minimum. In our first version, we supported nearly all of them. In fact, I did the encoding for all of them. All the mandatory fields are always there. So if all the messages that we have actually, the optional ones, they may not be there, but the mandatory, all of them, they will be there, and they are tested, right? And there is a code coverage also for them. So you don't need to worry about that. Both of them, we care about being multi-language. The approach is different. We do an SDK in C, and then from there, actually, with Swig, we provide the interface. In their case, it's basically a gRPC, right? I mean, it's just at the socket level, different E2 nodes that they have been tested, Radisys, srsRAN. We support in BubbleRAN OI, SRS, Amarisoft, and Lighton. A memory footprint that it was done some years ago. I think that right now it will look even better for the MX rig, definitely. The MX rig was something like 5 times smaller, but I think it will be better. The E2 agent xApps latency, in the O-RAN rig, you can find it below 10 milliseconds, according to our experience. In MX rig, you can go below 1 millisecond, right? And regarding the service models, in O-RAN rig, they are embedded, as I said. You need to do it on the xApps level, while in MX rig, they are pluggable, they are extendable. You can create new ones, custom ones, relatively easy. So I want to point out FlexRig, like these 2 principles that they were there from the very beginning, and that we took this philosophy, right? Let me read these 2 quotes that I think that they resume perfectly well the idea of FlexRig. Increasingly, people seem to misinterpret complexity as sophistication, which is baffling. The incomprehensible should cause suspicion rather than admiration. So if you see something that it's very complex to do something, an easy task, I wouldn't call that a sophisticated system, right? Therefore, we try to make it as easy as possible in MX rig and in FlexRig. I mean, we did the same. This first quote is for Niklas Beer that he passed this year. So I wanted to put it here. The other quote is from Tony Hoare. Maybe you also know him. And basically what he says is there are 2 ways of constructing software design. One way is to make it so simple that there are obviously no deficiencies, right? And the other way is to make it so complicated that there are no obvious deficiencies. The third method is far more difficult, right? A lot of managers, they believe it the other way around, right? At least what I have found during my career. If you go with a very simple solution, they will think that it is easy. While if somebody goes with something complicated, they may think that it has been difficult. No, in software, to do things simple, it's difficult, actually. So now let me go and show you here a demo regarding the latency of MX rig, actually in M80 in Ryzen, right? Relatively new CPU. This is a standard deployment, right? Then I will show you in an ARM-based architecture in the Cortex A76. This is basically thought for small cells of femtocells. If you are thinking in deploying something like that, so we also support these kind of platforms. I also want to say that this Cortex A76, maybe you are more aware of it, or maybe the audience is aware of Raspberry Pi 5. They do have this kind of core. And the third one is going to be on a Snapdragon X Elite Orion CPU, which is a very new CPU, actually, developed by Qualcomm, that they wanted actually to move forward in their market and try actually to go from the embedded to the laptop markets. So right here, I am connected to a Raspberry Pi, right? Let me run here the emulator. So this is the agent. We can think of it. This is exactly what it is embedded on a RAN. So when you run, for instance, OAI with the E2 agent, is exactly the same code. It's exactly the same code, and what it is going to be different are some function pointers for gathering the data. So when you do a request for data, right? At the end, we will call some function pointers. Here we will fill it with demi data. In OAI, we will fill it actually with real data. But I want to mention that software is exactly the same. So we need the rig, right? So we are connected, and let's run one xApp and see which is the latency on this system, right? So, right, yes, we are seeing it correctly. This is the latency from the moment that the message is generated on the E2 node until it arrives to the xApp. So it goes E2 node, rig, and from the rig, it moves to the xApp. We are on the same computer, so this is for an embedded system, right? But we can see that we are on the 100 microseconds, maybe 200, right? We can achieve this kind of latencies. Let's see in an AMD actually how it looks like. So again, we start the E2 agent. Let me start here the rig. So here we connect, and let me here run the xApp.
I had no idea about that at all.
So here we can see also that we are even faster, right? I mean, the cores, they are a bit more advanced. But you can imagine the kind of things that we can do with this embedded system, or when we put directly the rig and the xApp very, very close together. Let me stop sharing, and I will share my screen just in a second from my Windows machine. So please stay here. Let me. Well, apparently, it tells me that host disable attendee screen sharing. I don't know if we can fix this. Well, apparently not now. Wait. Okay. So let me continue, and we will come back maybe later, and I will show you actually how it looks on the newest Snapdragon Elite X. But I can advance you that it looks pretty much like the MAD Rise. So what I wanted to say with this is that complexity is not sophistication, right? And I think that this message is important because a lot of people, they get confused. And I have seen a lot of confused people in our community. Also, that better architecture, it means lower latency, lower complexity. It's always easier to extend, right? Which is always nice to work on. A better architecture, it also lets you have a variety of deployment options, right? So you can do from femtocells to macro cells, and you can do it on ARMS or x86, which is very nice. Also, better maintenance actually is very important for the projects, right? A proof of concept is not a production-ready solution, right? And we can go to a conference, we can show something, but definitely we need to test it. We need to care about security, other sanitizers. These things are important. We cannot ignore them. We do take this very, very seriously, actually, at BubbleRAN.
Mikhail, we upgraded some of the permissions. Could you try again and see if you can share the screen on Windows machine?
Oh, wait.
Yeah. Otherwise, if it didn't work again, you could just pass over it. It's fine.
Yes, no, if not, we can. Oh, yeah, it looks like I can now.
Okay.
Yes. Can you see it?
Yes, please continue.
So cool, here on the same way I'm doing the agent. Here the rig. So here there is the connection. And here we will write the xApp to see the latency. It's a bit worse actually, the AMD. Yeah, but anyway, it's definitely below 1 millisecond. So this was my this was my message actually. So yes, I was here. Better maintenance. I mean, it's easier to have more scenarios. Regarding security and memory safety, as we said,
Mikhail, sorry to interrupt, but your screen is black. Could you reshare?
Oh, sure. Let me share it again. Okay. Can you see my screen now?
I'm not sure because it's still, I think it's a black screen.
All right.
Yes, now we could see your screen.
Okay, perfect.
Please go ahead. Thanks.
Okay. So yes, I was just going through these points. And as use cases, having a better architecture and a better maintenance of the code, actually, it allows you to go through to use use cases much more easily and seamlessly, right? Okay, so now I'm going to move. So I have shown you the MX rig latency. I'm going to try to talk about which are the pillars in the O-RAN rig right now and their service models. So there are 3 pillars. As you probably know, here on the right side, you can see the 3 Greek columns, yes, the Doric, the Ionic, and the Corinthian, right? In the same sense, we have the key performance measurements, which it was the first one, the oldest one, and it is used to gather statistics from the E2 node. You will see a demo, actually, multi-source and multi-vendor demo. So we will use OAI, srsRAN, and Amarisoft to form a data lake with this KPM. The second one, that it came a bit later, also on time, in the timeline of standardization, is this Ionic column that it's the RAN control. So you can fetch some data, but especially the idea is to control the RAN. Here we can have, for instance, slicing handover. These are the 2 typical use cases. You will also see 2 demos of this. You will see OAI and srsRAN RAN slicing using the RC, and you will also see a demo of a handover using Amarisoft. And finally, we will go through the 4th demo regarding the service models, which is the cell configuration and control. It has been the last one, right? The most refined one, if you want to say it like this. It's about the configuration and control of the cell itself, and it's about changing basically the bands on the frequency where you work. So you can do this like offline, the IRFCN, or you can do it like online with the bandwidth parts, right? In this case, you are going to see also a live demo of the dynamic bandwidth part reconfiguration using CCC, and this time we will use Amarisoft for it. So KPM is the basic, yet it's an essential service model, right? I mean, without data, we see nothing. There are more than 900 measurements defined between the O-RAN and 3GPP spec. Here we are in a situation a bit also, we will need some help also from the community, in the sense that right now there are like 6, 7 measurements that are there. And we ask the community asks us like, we would like to have more measurements. And then we ask back like, okay, which one? So we will implement them. And then they basically come back and we don't know because we still don't have the use case, right? So this snake that it bites its tail, we need to also to somehow go through, and we are thinking about this also on BubbleRAN. We hope also that if we show to the community more use cases, this will naturally also evolve. Anyway, the KPM, it permits data gathering from heterogeneous networks to form these data lakes that are basic for machine learning and artificial intelligence nowadays. We currently support OAI, srsRAN, Amarisoft, and Lighton. We also offer as databases SQLite, MySQL, and TimescaleDB, so that you can store all the data for further processing. The idea on the xApps is that we are multi-vendor, write once, run anywhere, like this slogan of that was famous of Java back in the 90s. So, and basically the xApp, you can subscribe to gather information from the E2 nodes with some periodicity. Let's say like I want data every 1 millisecond, or I want data every 100 milliseconds. From the E2 node until the xApp, you are going to see in the demo that you can achieve relatively easily less than 1 millisecond of latency on average. For this demo, I'm going to stop sharing my screen, and I'm going to let the floor here to my colleague, Kai.
Okay, hello everybody. My name is Kai. I'm going to show you the first demo of the day. Yes. So, the demo I'm going to show you is the KPM monitoring xApp. In this demo, we're going to use 3 different vendors: srsRAN, Amarisoft, and OAI. And all 3 of these GNOB are going to connect to one core network. Also, is from Amarisoft. Alongside with all these GNOBs, we're going to use QuickTel module, Pixel phone, and a QuickTel module. So, in order to gather the data, we're going to use one monitor xApp to get the data, and one database MX data to store the database. And I'm going to use Grafana to show you the log of how the data going to go inside the database. Okay. So, in the video, I'm going to show you, sorry. Okay, in the video, first I'm going to turn on the Amarisoft core network, GNOB, and a Pixel phone. On the screen, I'm already turned on the Amarisoft RAN and the core network, and also I'm already connected the UE. Here I'm trying to turn on the proxy agent. Sorry. Yeah, I'm turning on the proxy agent, which is a E2 agent for the Amarisoft. Yeah, you already see that the core network, the UE is already connected to the core network. I'm going to do the same procedure for the OpenAirInterface. I'm turning on the GNOB and also connecting to the UE. Yes. I'm so sorry for the technical issues.
Don't use the arrows. Don't use the arrows. Just use the. Don't use the arrows. Don't use the arrows.
Okay.
Just use your mouse. Use your mouse.
Okay, again, here's the screen for the OpenAirInterface. I'm turning on the GNOB again. After that, I'm connecting to the UE. the same procedure is going to apply for srsRAN. But however, on the documentation, they require to turn on the near real-time rig. So first, I'm going to turn on the rig. And you already see here that all two of the GNOBs are already connected. After that, I turn on the GNOB of Amarisoft, of srsRAN, sorry. Okay, so before I go into the turning on the monitoring xApp, I'm going to show you the configurations that I have defined here. So for different vendors, for OAI, I set the timers, the internal timers is 10 milliseconds, Amarisoft is 50 milliseconds, and for srsRAN is 300 milliseconds. In here, for both OAI and Amarisoft, I put KPM parameters is PTCP downlink, uplink, EV throughput uplink and downlink, and PRB downlink, uplink, both for Amarisoft and OAI. But for srsRAN, I put EV downlink and EV uplink just for the example later. I'm going to show you in the Grafana. Here, I'm turning on the xApp, and you can see you have the log of the different GNOBs, different vendors. You can either see the log in the xApp log, or you can go to Grafana, which I'm already have here. So in here, for your informations, all three of the GNOBs are monolithic, so there's no DU and CU here. In these Grafanas, we have six log for the 6 KPM parameters. Besides from these 6 log parameters, there are 2 different logs, which is average latency from each node to xApp per second, and a data rate that xApp going to query inside the database. As you can see here, I'm trying to move back a little bit seconds just for getting the data. You're seeing here, there's no data coming in because I haven't generated the traffic. But however, I'm going to go into different vendors' name. First, the Amarisoft. You can see the latency is really low. srsRAN is the same things, below 3 microseconds. Yes. And then, okay. After that, I'm going to generate traffic. So in here, I'm going to generate traffic, uplink for Amarisoft EV, uplink for Amarisoft EV also, for the OAI. And for the srsRAN, I'm going to do the downlink. Yes. So going back to the Grafanas, you can see that the traffic is already generated. Yes. In conclusions, for this demo, we're using MySQL as the database, but BubbleRAN also support for two different databases, Timescale DB and SQLite. Furthermore, you can use containerized xApp for your data sources in order to create a data lake. Yes. Okay. Thank you. Back to you, Mikhail.
Hi, Kai. I think that you need to stop sharing. Yeah, right now. Thank you very much. So can you see my screen? No, we cannot. Let me try it again. Okay, now it looks like it is working. So, which is this takeaway of this demo? Basically, that KPM is essential for data gathering, as we have just seen. If we want to form these data lakes, that they are essential for 6E, actually for training, for data collection, and for basically gathering information from different data sources, KPM is definitely our first option and our service model. We have also seen in this demo that a single xApp operating over multi-vendor deployments, it works out of the box, right? We don't need to write 3 kind of xApps. You could extend here. We didn't show this, but you could actually have another OAI-RAN, another Amarisoft RAN, another srsRAN working, and the xApp wouldn't change at all. So the key performance indicators probably from this demo are that the rig permits a wide range of use cases with different periodicity, as my colleague Kai showed, right? There were like 10 milliseconds, 50 milliseconds, and 300 milliseconds. So basically, we are asking for statistics every 10 milliseconds, every 50 milliseconds, or every 300 milliseconds. We also showed in this demo, we could also see that the latency was pretty low, below 1 millisecond on average. I also want to mention that MX Rig, it goes beyond KPM. It permits easily, you can customize your service model, right? And in fact, you can actually process the data on the GNOD or on the xApp. The idea is that right now in 3GPP, you basically need to process this data on the GNOD, for instance, mean throughput, right, of the RLC or so on. But maybe if you have enough bandwidth, you don't want to process it there, or maybe this data does interest you for some other purposes, right? So you can actually just send it. So if you do if you customize our service models, you are able to do this. And if we think a bit about O-RAN and 6G, like in BubbleRAN, we are trying to evolve towards more layer-based and fine-grained programmable measurements. And we are thinking here about sensing, localization, physical layer, right? All these things that they are not there and still they are needed for 6G and for its use cases. Also, we have a multi-source data lake that is called MX Data. So we provide the infrastructure, right? Everything is O-RAN. We can also think about energy efficient use cases, actually. Yes, and said this about the KPM. I will now let the floor to Chi, and she will be presenting the second column, Greek column, right? Here on the service models, and that is the RAN control. So I let you hear the floor, Chi.
I need to share the screen. I cannot share the screen. Oh, okay, perfect. Okay. Okay. Hello, everyone. My name is Jiejun. I will present the O-RAN RAN control service model. And okay, so the RAN control service model is a service model defined by the O-RAN to specify control the radio access network in the near real-time or non-real-time domain. And this service model is enable remotely controlling the RAN for 5G and 6G use case, including the radio bear control, radio resource allocation control, and connectivity mobility is referred to the handover, and the radio access control or dual connectivity dual connectivity control, and also the idle mobility and beamforming configuration control. So by using this RC service model in here, we can optimize the performance of the RAN in the context of the QoS guarantee, load balancing, and the energy efficiency. So our MX rig currently can support the radial resource allocation and also the connecting mobility control. And we will show two demos in this section. The first one is we will show one xApps doing the slicing by using the RC radial resource allocation control two different GNOB from two different vendors, one from OAI, another from srsRAN. And the second demo is we will show one xApps doing the handover across two different GNOB to hand over the UE across two different GNOB, and the GNOB is from the Amarisoft RAN. So I will show the first demo for the slicing. So this is the demo setup for the slicing. So from the picture, you can see there is one xApps in a picture in here, which will control both GNOB from OAI and the srsRAN at the same time. And this xApps is maintained not only to support multiple slices, but also for multiple E2 node, which is also can control multi-cell scenario. So in this xApps, I create three slices in here. And the first slice, which is support the SST1 and SD0, which is the configuration for the first UE connected to the OAI. And the second slice is using SST and the SST1 and SD5, which is configured by the second UE using connected to the OAI. And the third slice, I will create one slice in the srsRAN, which will change the resource ratio in the SRS GNOB for this specific UE. So let's move on the demo in here. So from the demo video, you can see I will run the OI connect work first, and after I run the OI GNOB, after that I will run the near real-time rig at the right side. After that, you can see, okay, the E2 setup already sent to the near real-time rig. And I will start running the OI first UE. From the video you can see the first OI UE is set to the SST1 and SD0, which present as the first slice. So I run the first UE, and after I check the configuration for the second UE, you can see for the second UE, the slice configuration is set for SST1 and SD5, which is represented as the second slice in here. So the second UE also connected to the OAI now. So I will start generate the downlink traffic for both of UE in here, from the core network to the end user. So both of UE get around 90 megabit per second downlink throughput. So after that, I will start running the OpenFireJS core network for the srsRAN GNOB. So by to deploy this setup, we following the default vanilla version of the srsRAN. And the srsRAN GNOB in here, we are using the latest master branch, and the OpenFireJS is by following the deployment shown in the srsRAN tutorial. So now we run up the OpenFireJS by Docker Compose. And we will run up the srsRAN GNOB. So after we run up the srsRAN GNOB, you can see it connect to the near real-time rig too, and it registered two service model. One is the KPM, another is the RC. So I will start running the SRS UE. So the UE is start connecting, and so this is why there's some static showing in the GNOB side. So I will also generate some downlink traffic from Open5GS to the SRS UE2. For the SRS UE, the throughput is downlink throughput is around 26 megabit per second. This is because the configuration for the srsRAN GNOB is set for 10 megahertz bandwidth, and for the OI GNOB is set to 40 megahertz bandwidth with 30 kilohertz subcarrier spacing, and for the srsRAN is with 15 kilohertz subcarrier spacing. So I will start running the xApps in here. So after I run the xApps in here, you can see the throughput start changing. So we can look in detail about what control message I send in the xApps side. In the xApps, I send 2 control messages. One is sent to the OAI, another one is sent to the srsRAN. For the OAI, I create one slice which is use minimum ratio 30, maximum ratio 30. And for the second slice, I create minimum 70 ratio and the maximum 100 ratio. And for the srsRAN in here, we create one slice with minimum 5 and the maximum 10. So from a result in here, for the first UE, you can see originally is around 90 megabit per second. And it goes down to around 45 megabit per second because the first slice is configured to use only 30% of resource. And for the second UE in here, originally is 90 megabit per second, and it increased to around 115 megabit per second. It's because the second slice is configured to use at least minimum 70 resource from the OAI, and it can reach to maximum 100% if the first slice not use any resource. And so for the third slice in here, since we configure the minimum 5, so the throughput in the third UE dropped from 26 megabit per second to 6 megabit per second in here. So this is the demo for the slides, and I will give back the floor to Mikhail to show the second demo for the handover. Mikhail, could you share the screen?
Hi, Chi.
Yes.
Yes, I think that you can see it now.
No, we cannot see the screen.
You cannot see the screen? Yes, I think that you can, right?
Maybe you stop sharing and resharing again.
Can you see it or you cannot see it? You can see it, right? Okay, I will think that you can see it.
No,
If not,
Mikhail still is black.
still is black.
You mute you.
Okay.
Mute and
Let me
yeah.
try it again. Now
It
maybe.
should be fine. Yes. Thanks.
Thanks to you. So let me go here through the second one that is regarding the handover. This handover, it will happen actually in Amarisoft. So it's relatively simple in the sense that here we will see the cell, right? It's in the band 78. You can see it here and the frequency, right? 632.778, right? And we have one UE connected, right? And we can see it on the right from the UE that there is a ping going. Okay. Now you can see it here again. we can go now to the, basically what we are going to do right now is we are going to connect the proxy agent, right? So since Amarisoft does not support E2 interface directly, what we have is a proxy agent that basically it converts WebSockets, that is what Amarisoft talks, and E2 AP, right? So here we have connected, here WebSock handshake successfully completed. And now we are going to run actually the other agent, of course, because we have two base stations, right? Here we wait until we connect both of them. Here they are connected. We'll run the rig now. Sorry, I don't know what happened here. So yeah, we run here the rig. Here we are connected to two E2 nodes. We run now the xApp for the handover. And here we can see actually that the time between when we send the message control from this machine, right, that is IO, it needs to go to Vinci, where it is the E2, the proxy agent. And from Vinci, it needs to go either to IO again or to O-RAN for sending this handover. The timing, it's 35 milliseconds. So this is the round trip time of the control message. We had here before one UE. The UE is not connected here anymore. The UE is connected to the second base station, as you can see, right? And here on the right, you may have seen a little increase on the delay of the pin. This was due actually to the handover, right? So this is the handover demo. So the takeaways of this demo, of both demos actually, is that the RC permits controlling the RAN as well as monitoring it. Actually, on the handover, I didn't explain this, but in order to know which UEs are where, I sent a message that is called RC on demand, that basically will just, it's like a subscription, but just for one message. In this case, I ask, I want to get the data of which UEs are connected there. And with this data, actually, then I knew from which base station to which base station I wanted actually to switch to jump, right, to the handover. So we have a single xApp, and it can operate over multi-vendor deployments. This is especially true actually for the slicing demo, right? We have seen it with OAI, but also with srsRAN. And we basically do support the slicing and handover right now. We have real-time control messages. I mean, we have less than 2 milliseconds for the slicing demo. In the slicing demo, it was something like maybe it was something below 1 millisecond and something like above 1 millisecond, but very barely. We can control the RAN across different vendors. And we can think of these ideas of load balancing, right? We want to trigger some UEs to one base station or the other one, and this could be due to energy efficiency. And this goes beyond mobility. It's not that I am just moving, right? The signal strength, it goes down and I do naturally the handover. We can force it, right? And we can play with this. So it's a really powerful, really powerful service model in this regard. We also support custom slicing service model. I think that she could give a talk about this, a webinar of 2 hours by herself. We do support, for instance, asymmetric uplink and downlink for slicing. We support also different slicing algorithms, MVS, EDF, enhanced EDF, policy-based. And we also support what it's called a slice operator. So the idea is that we do the slicing, right, from the application to the network to the radio. So we, through all the pipe of the message from the DNN actually up until the application, we can actually reserve some or apply some slicing policies for it, right? Now let me talk about the last one, about the cell configuration and control, which is the last column, like in like the Greeks, right? It has been the latest addition in BubbleRAN. It is missing actually in the open source FlexRig. This is a pity. I hope that we will see it soon, also coming for the open source. It is a key third pillar to do the reconfiguration of a cell or of a node, right? You can do it offline or online. Offline is basically the configuration of the bands, basically, and online is about the bandwidth parts, right? The bandwidth part is a procedure to configure the channel into multiple smaller segments. If you know about the narrow band in LTEs, it's pretty much the same. Or I think that it was designed with this purpose. You can have up to 4 bandwidth parts defined, but only one can be active at a time for a given UV. The idea is to save energy for devices where the full bandwidth is not required, but energy consumption does matter. We can think of IoT devices, for instance, right? We don't want to have all of, we don't want to be available to have all the frequency, right? We can just get the IQ samples of smaller part of the frequency. It can also avoid the interference if actually you have 2 cells that they are on the same band, quite close. You can also like tell the UEs to split. And you can see here on the pictures, which is the idea, right? Basically, you will say like this bandwidth part. So this kind of frequencies is the ones that I'm going to use, and I don't really need all the band that it is given to me. So I'm going to go through a live demo for this. On Sonic, we will have iPerf and the Amarisoft core network. On Azure, we will have an xApp, the near real-time rig, the proxy agent, and the Amarisoft RAN. And we will also have a Google Pixel for it. So let me come here to the machine. So here we are. The G-Node is on. Let's see. Oh, let me see if I can. No, it doesn't want to. Wait a second. I mean, it looks like it's dummy.
Mikhail, maybe you close the window and then open it again from white.
Yeah, let's try it again.
Okay, fantastic.
Okay, so it's now connected. Okay, perfect. So let me see if it is connected, and yes, here we are, connected. So let me run here the proxy agent first. Let me run the rig. And actually, let me see if this is, yeah, so here we have an iPerf server. So if we start it, here we will see the bandwidth that we have right now. Right, this depends on the MCS and so on. Now, what we can do actually is we can send here an xApp. The first parameter, 1 or 2, it depends if you want uplink or downlink, right? Here, the second parameter, it will tell you which is the start resource block. And the last parameter, it will tell you how many resource blocks, right? So if we just send this command for control, we should see now like, okay, at the beginning we had, I didn't explain this, 50 resource blocks, right? And now we have something like 5. So here you can see actually that the bandwidth, it went down on the UE. Let me try to do it again. right? So here we are again on the first situation with the full bandwidth. We don't have the best modulation and coding scheme right now. This may happen, but here you can see that the bandwidth is much better. Another thing that you can see here is that the control loop is something like 10 milliseconds. So basically the message, it went from IO here to Vinci, that here we are running actually our proxy agent. It came here into this machine that is Roland. It came back to Vinci, back to the rig, back to the xApp, 11 milliseconds. This is the timing for going and responding. It doesn't mean actually that it was the configuration was done, right? But the configuration, it will just need some more milliseconds, but not many actually. So that said, so this is the live demo. Actually, it was also, we also have a video. So if you wanted to look at it later, we could also share these videos. The takeaway of this CCC, that it's our latest addition actually, is that we support the bandwidth delay parts for online reconfiguration. And then here, my colleague Ilias later will show also how we can do offline band reconfiguration. So actually, we have more configuration and control are possible. This is what it is extending CCC with. The latency for the bandwidth part configuration, it will be below 50 milliseconds, right? And we can see a seamless connection and service continuity, right? This is what we saw. For instance, thinking about O-RAN and 6E, there will be not a conflict, but we will need somehow to control. So the control, the management plane actually is normally the SMO, right? And this is the CCC, which is the rig, which in theory it's not its part. So this distributed management in 6E, we will need to come to a solution for that. We have done in the past for things that they are similar. For instance, for TCP. TCP is also a well-known distributed algorithm, and it works very well. So we should come to something there so that we can work with the management plane and the RC at the same time. And if you want actually a finer grain, like a slicing, really, you can do bandwidth parts and slicing, right? Because bandwidth parts is about the frequency chunk, right? And slicing is about the resource blocks that you wanted to give. So you can also play with both of them to go a bit beyond what it normally it's called slicing on 3GPP, that it doesn't talks about the frequency that they are reserved. So the overall takeaway before the break is that the KPM, RC, and CCC are the three necessary pillars to monitor and manage the RAN. And in this regard, I think that MSRIC has the most feature-complete ecosystem, actually, based on the FlexRIC open source project. As KPIs, I think that what MXRIC does give to the public is low latency control loops, so that you can think of different 6E use cases, actually, because you can gather information with KPM very fast. You can act with the RAN control also fast, and then actually the RAN, the configuration, it will take some time on the G-node in itself, but we are talking about very, very few milliseconds. While in O-RAN, you know, the limits that they talk just for the rig, they are 10 milliseconds. So the O-RAN rig is not valid actually for these use cases. I also want to emphasize that the MXRIC, it does support multi-vendor deployments. This is very important. From industrial grade, right, to simulators. You have seen it with real phones, Quectel modules. But you have also seen simulated UEs. So in this spectrum, we support all of them. And if we look at 6G, right, and what is about to come in the future, we think that these 3 service models, they are necessary, yet may not be sufficient for 6G use cases. We think that we need to go a bit beyond that, which we will try to dig a bit on the next hour. And regarding, well, the table here, you can see actually what is implemented where. To be done is something that we have in mind in our roadmap, actually. So at some point, it's very, very probably we will assign resources for getting that. Not available is that we didn't think for the moment to assign resources, but this may also change in the future. And with this said, I will give here the floor to Alireza. I think maybe he wants to give a couple of words, say a couple of words before the break.
Yes, thanks, Mikhail, for the presentations. Yes, as you mentioned, right now we are at in our time zone, Central European Summer Time. We are 6:20 p.m. We are going to have a break for roughly 5 minutes, so we come back in 5 minutes at 6:25. In the meantime, we would stop the recording, and then I would start the recording again after we are back. See you in 5 minutes. Take coffees, take a sip of water, and then we see. You could continue asking questions in the chat. We would continue responding. Thanks.